Swayam Prabha. Digital India. Educated India.
Welcome back. Lecture 28 is on machine learning typology. That is, what are the different types of methods or models that are there that we will study in this course. So, the concepts that we will cover will be the different machine learning typologies, the different machine learning models, then supervised learning models, unsupervised learning, the concept, and then unsupervised learning models, semi-supervised learning and models, reinforcement learning and models, and neural network-based learning. So, by machine learning typology, we mean that, what are the different approaches towards solving different problems that we face related with data analysis using machine learning models and all, and what are the different approaches or rather ways to solve it. So, different problems require different types of learning approaches, and also there is no universal model that could be fitted to any kind of machine learning problem. So, according to the problem, according to the nature of data, according to the solutions we want, or according to the context or what kind of work that we are doing, we will be using different kinds of models. So, first of all, the model classification could be varied based on the availability of labeled data. That means if we already have input as well as output data, then only we can go for this kind of models. Then it can depend on the nature of the output variables. If the nature of the output variables is categorical or continuous, depending on that, the model choice would be different. And finally, the learning mechanism. So, depending on what is the learning mechanism, we will say there we can have different kinds of models. So, first coming to the most important one, of course, is the learning mechanism. That means what is the kind of theory that is applied to solve that particular problem. So, the first one is, of course, supervised learning. In this case, we are learning from the labeled data. That means we have got two sets of variables, x and y. X is being predicted and y are the predictor variables. That could be multiple features, of course. There could be many y1, y2, y3, y4, many variables. But from a set of existing data set, we have a set of data where we have got both the label as well as the predictor variables. So, in that particular case, what happens, we will call it a supervised learning. And in this case, the two different examples you will find again and again, that is regression models and classification models. These are the two groups of models that you will come across. Then is the unsupervised learning. That means here there is no label as such. That means we have a set of data, but we will try to find patterns within it, right? What happens together, or which things are nearby, which things are far away, and so on. So, we will try to find patterns in unlabeled data, and this is where you will come across models such as clustering models, dimensionality reduction models, and so on. Then there are semi-supervised learning methods. That is where for the entire data set, we don't have the labels, but we have labeled data for some part of the data set. And then we use some techniques or strategies to, solve the overall, predict for, or rather develop a model which will be able to predict for, any kind of data set based on those limited number of levels which you have got in a training data set. Then reinforcement learning, it is learning through interaction and reward. In the last lecture, we were discussing a bit on this. That means what we need to do is, that means the machine learning algorithm trains itself so that it does different things to test which one gives it the best possible reward, following a set of rules or policies. And that automatically creates a set of, given a certain problem, the machine will know that these are the likely test which will give me positive results, and accordingly those steps would be applied. So, that's a reinforcement learning model. Now, the other way to classify is, of course, based on the output. Some of the machine learning models will have a continuous output. Usually, we find it in form of regression models. That means we can predict a continuous variable at the end of it. So, using some features, I can predict the actual value of a variable. the other continuous value of a variable, and the other is a classification model where the output is categorical. That means this particular that it would belong to a particular class. Then there are models which looks into ranking or prioritization. That means or we call them ranking or recommendation models, where if we can find that okay, which kind of things needs to be prioritized, so we can predict the rank of those things. Then there are also machine learning models based on data types. That means on what kind of data we are dealing with. That also is important because the pre-processing and also some the intermediate steps of the model will depend on that. So there could be basic tabular data models. That means data is in form of tables. Then there are spatial models where the data is also having some additional features like GIS-based features on latitude, longitude, spatial location. Then there are image-based models where we are using image data, we can generate information or we can do analysis like using in case of CNNs. And then there are time series models where there is obviously there is a sequence involved, and that's also as per the time. So this is where LSTM, ARIMA, this kind of models comes in. So in addition to this, again and again we will come across the term neural networks. That means this itself is not a typology, but it's a flexible model architecture which can be applied in supervised, unsupervised, semi-supervised, or even in reinforcement learning models. So that means it's an approach in which we can use to solve different kinds of machine learning problems. And then there are another way to classify machine learning problems is models which are interpretable and the models which are black box. So again, this I've repeated in the earlier in the previous lecture. We have explained this in the previous lecture where we said that interpretable models follow some clear and logical steps. They follow a function and all, and we understand what is the the background mathematical function, the loss function, what strategy has been utilized, and we know that how we have arrived at this particular decision. So linear models, decision trees are all in those falls in those domain. Whereas there are also black box models because in some cases we have so much data, we have to make sense. So a lot of abstracting of the data has to happen, reduction of the data has to happen, and then complex relationship has to be established. So such as in case of deep neural networks, some ensemble techniques and so on. So where we require high accuracy, but transparency is not that important. That means we require the prediction to be very, very near to the actual values, but we don't that much bother about how we arrive at that particular prediction. So this is a visual representation of different kinds of models that comes under this typologies. That means first of all we divide for this particular course we divide the machine learning techniques into 5 groups: supervised learning, supervised learning, semi-supervised learning, unsupervised learning, reinforcement learning, and then neural networks. So neural networks, as we have discussed, it pans across all these different groups, but we will give some separate examples of this. Now, on the other side, what you see is a more interesting representation of how these are all related. So, for example, you can see supervised over here. So, it is one branch of machine learning, you can say, where we look into classification task, regression task, and also some amount of dimensionality reduction task. That means we will regression, as you know, classification we have already discussed. Dimensionality reduction is when I've got a lot of set of data, high dimensional data, I just want to reduce features, or I want to take the meaningful features which will have more impact on our model. So that is dimensionality reduction. Then reinforcement learning models. Before we go there, there would be unsupervised models. That is, dimensionality reduction is also there in unsupervised as well. So that means in this case, we don't have the labels. Then there are clustering models, and then there are association-based models, right? So we try to find out which things are related together, right? So that's the association model. So like, for example, when you shop something, then you get recommendation of other things, right? So those kind of things are sort of association models. Then in semi-supervised models, this is somewhere, as I told, that only partial part of the data set is labeled. And so here there are some models like level propagation, level spreading, self-training classifiers, which we will discuss in detail further. And then comes the neural networks. Then there are different broad groups of programs which comes under that, such as encoders, where both input and output is encoded and all. And then there are generative adversarial networks where we generate new information, new solutions. Then recurrent neural networks, somewhere time is important, right? So we follow most time series models comes under this. Feed forward neural network standard, how we gradually revise the weightages given to the different parameters. Convolution neural networks has to deal with all images and those kind of classifications, which or certain kinds of detection task which has to be done based on images. Then coming to reinforcement learning, there are different kinds like Monte Carlo methods. For example, Monte Carlo methods, the entire learning task, once a machine trains itself, we can only create the final, values of reward and all these things once the entire thing is done. That's in case of Monte Carlo methods. Then there is Q learning, which is the most common one. Then there is deep Q learning, where we use neural networks along with Q learning. And then there is SARSA, state action, reward state action. You can understand that based on reward, the action and all these things are modified. And then proximal policy optimization, policy gradient, temporal difference, and so on. So this is more or less not covering everything, but at least it shows the different types of models that we usually use. Now, we will elaborate on each one of this. So, first of all, let us talk about supervised learning. And supervised learning uses both historical labeled data to learn about the predictive relationships, right? So, that means there are input-output pairs, and models learns by mapping that to input with output, that is x to y. And there are different types, of course, and again it depends on many things. It depends on if the outcome is continuous, outcome is categorical, or it depends on the task itself, and so on. So the first one is, of course, the regression task. That means we are predicting something continuous based on the different values of y. We are predicting a continuous value of x, and so we are primarily predicting a value, that is a magnitude or quantity of that particular aspect. Now, what are the models involved? Linear regression. We all know linear regression. I've been discussing that as well. We in univariate, we showed you a single variable relationship between two variables, and more or less it is it follows a straight line. Then there is Weege and lasso regression. Particularly this what it does is it extends linear regression by adding penalties that reduce overfitting and improve model robustness. That means it adds a penalty term where that means if the model is overfitting or is it, then it will have a more penalty, and that will actually help us to determine a better model. Then there is random forest regression, which we will be explaining as well. Like for example, I will be explaining it along with this part over here. Why? Because this random forest part, decision trees and random forest are actually two variants of the same thing. That is, the decision tree is the base model, and random forest is the ensemble technique where we use multiple decision trees to predict, right? So we will come to that. So you see, the only difference is over here, this one comes both under a classification task as well as a regression task. So why it happens like that? This is because suppose I am classifying something, right? For example, I'm classifying the height of individuals in class, right? So that means I can have high, low, medium, something like that. So there are three categories. Now, if I say that, well, my categories are so small, it is like the, it's like a continuous variable. That means I will predict that group one is people with height 4, then 4 feet. Then the second group is 4 feet 1 inch, 4 feet 2 inch, and so on, right? So in that way, we can almost predict height like a continuous variable. So that means random forest could be utilized, or primarily many classification models could be also used as a regression model as well. So then there is gradient boosting as well. Gradient boosting is regression improves predictions by iteratively adding models that correct the errors of the earlier one. So that means different model specifications are being for every regression. Any regression line, the beta values can be changed, and we can have different specifications. And each one will result in different sort of prediction errors, and we can keep on modifying it till we reach the best one. So that's the gradient boosting regression. Now coming to classification task, mostly we deal with discrete or categorical output. That means either it predicts in independent values, or it could be a category like which are related. There is a sequence as well. That means it could be like three categories, like three vegetable categories. Whereas it could be also categorical, means we can say different levels of importance or different levels of satisfaction, something on those lines. Now, in this particular case, in classification task, we actually assign labels or probabilities to each of this, so that we predict that either this particular item with these features will be falling in which particular class. So here we have got logistic regression. So basically, it's a probabilistic classification, of course, which estimates the likelihood of class membership using a logistic function. Now, the question is, we will, of course, look into these models and the workings of these models in detail later. But what I can tell you is, we estimate probabilities of a particular particular item to fall in a particular class, right? So that's a logistic model or a probabilistic classification model. So in this particular case, we use a logistics function. Unlike a linear regression where we reduce the root mean square errors, here what we do is we maximize the log likelihood of a particular utility functions. So we using utility functions, we can formulate a log likelihood function and we maximize that. So we will learn about these things later. Then comes the the k nearest neighbors, then support vector machines, then decision trees and random forest. All these are different types of classification tasks which we will eventually take up. Now, the decision tree is something which we will again and again use in our planning for taking many decisions. And it is basically a classification task, but it is a much more simple way to do that. And at the end of that, we also don't have to have very lot of assumptions in this model. That means if the data is very nonlinear, and it is a mix of different kinds of items, categorical, continuous, then we can go for decision tree to classify. So decision tree predicts the outcomes by following a sequence of hierarchical simple if-else rules learned from data. So that means if this happens, this will happen or this will not happen. So those kind of rules are there. And once I keep on, asking the questions and then we ask questions, whatever results comes, and then we take that up and then ask questions further, eventually we will come to a grouping which is almost homogeneous. That means entropy is less. Or we can say it will come to individual value in case of regression. So that's the approach of developing a decision tree. Now, random forest and gradient boosting are ensemble methods. That means it's a mixed method where we are mixing different kinds of methods together to come out with that final solution. So it's an ensemble of random forest is an ensemble of decision trees, and that means we are taking several decision tree models. And then we can improve the prediction accuracy by averaging the output of all the different trees, and also we can reduce by average, and also by reducing the variance between the results. Now, gradient boosting is a similar ensemble technique that builds trees sequentially, but what happens over here is every time a new tree is being built, we correct the errors of the previous one, and then we move forward. Now, along with that, we also have got support vector machines. Support vector, it's a margin-based classifier. Again, it's a classifier that separates classes by finding the optimal decision boundary in the feature space. Now, it all depends on the loss function or the constraints which are defined to determine how the classification boundary will be formed, or the optimal decision boundary would be formed. So these are the different popular supervised learning models, and we will cover many of them in this particular course. And of course, we have classification and then we have regression. Both of this we have done in detail. We have KNN, we have extreme gradient boost. So this is another form of decision tree. Gradient boosted trees, adaptive boosting, random forest classification, decision tree classification. This is the simplest, most decision tree model. Then support vector machine, naive Bayes classifier, then logistic regression, and so on. Now, out of all this one is new, and it classifies data by estimating. Naive Bayes classifies data by estimating class probabilities using the Bayes rule while assuming independence between the features. So this uses the Bayes rule or Bayes probability Bayes algorithm to determine the split between the data. Then there are regression tasks. It could be regression models like linear regression models, random forest regression models, decision tree regression, support vector regression, locally weighted scatter plot smoothing, and multivariate adaptive regression, splines, and then KNN. So again, KNN is something which you will find in different in dimensionality reduction as well, right? So sorry, it is also not. Sorry, I'm mistaken. KNN you will find in also এই জায়গাটা একটু কেটে দিও. KNN you will also find in classification as well as regression task both. So when we will go into the classification task, you will also see that আবার এই জায়গাটা কেটে দাও, আবার ওই KNN থেকে শুরু করবে. KNN যেখান থেকে বলছেন ওটা কেটে দাও, KNN থেকে শুরু করবে. Then comes KNN, K nearest neighbor. It's a distance-based algorithm and can be used for both classification as well as regression, depending on how neighbors' outputs are aggregated. So this again could be used both for classification as well as regression. In addition to that, we also have got the dimensionality reduction. Primarily, you will find it in unsupervised models. And then you will see that over here, the linear discriminant analysis is based on labels. That means data has to have labels. So it is supervised. But usually the more common one is the PCA, which is unsupervised and preserves a maximum variance among the, and it preserves the maximum variance. Whereas in case of LDA, it's supervised and it maximizes the class separation. That means it maximizes that how the differences between the classes. So dimensionality reduction, as we have already discussed, it's a process of reducing the number of input variables. That means if there are many variables which are correlated together, they actually result in bad prediction. So we want to reduce. So which ones to reduce? So actually that could be done using this linear discriminant analysis. And so this is the different kinds of supervised learning that we can models which we usually will encounter. Then coming to unsupervised learning, obviously we don't have labels here. So that means we have a set of data and we are trying to make sense of the patterns that emerges out of it. And so we want to discover the hidden structures within this data. And in this case, we use both exploratory as well as descriptive statistics to determine that. So there are different kinds of models here. One is a clustering group of models. What it does is it groups in similar observations together. It can also go for spatial pattern discovery. That means if it is varying as per different zones or locations, particularly when we do heat maps and other kinds of things, we want to identify which zones show similar value and so on. So that part could be also done with clustering models. And different clustering methods suit different spatial and density patterns, and accordingly we'll choose which model to apply. So there is K-means clustering, there is hierarchical clustering, there is DB-scan. So DB-scan, as you understand, it's based on density, whereas K-means is based on distance. Hierarchical clustering is based on how we can group the different classes in a hierarchical form. Now, other than clustering models, there is also dimensionality reduction models. Like, we want to reduce the number of variables while maintaining the major, relationships of the patterns, and it aids in, visualization, and also it tells us very clearly what things comes together and which other things among these are not that related. So those has to be grouped, and in this way we can create hierarchies or groups of, how groups of this variables are together. And one main tool is, of course, PCA for this, principal component analysis. We will learn that in detail later. And then coming to association rules, this is another type of unsupervised model which identifies frequent occurring patterns among variables. And if sometimes it is based on rules like if and then statements, if or else statements, and sometimes it is based on co-occurrence. But whatever it is not for looking. It does not show causality. That means it is when things are together that only we are identifying. But why they're together, one influence other, that we are not, saying anything about. So this is then there is exploratory pattern discovery also, that is considered within association group of models. So one model is a priori algorithm, then another is EP growth, then there is ECLAT. So these are all different algorithms, and each one has got their own requirement in different context, and that we will discuss when we'll go into details of these models. So regarding the different clustering systems, k-means partition data into k clusters by minimizing the within cluster variance based on distance to cluster centroid. So that means how tightly things are packed together, that is being looked into. Hierarchical clustering, it builds a hierarchy of clusters using either agglomerative or divisive merging based on similarity. So one is bottom up and the other is top down. And then there is DB-scan, which is density-based spatial clustering of applications with noise. This identifies clusters of arbitrary shape and isolates noise by grouping densely packed points. So it is more about density of those points that is being considered. So this is the group of models we will again come across often. That is, within clustering, we will do mostly k-means, Gaussian mixture models, hierarchy HSC, which is hierarchical agglomeration clustering, then DB-scan, already we discussed. And out of this, Gaussian mixture model is new. It is basically a method of clustering using probability, or it's a probabilistic clustering method. And what it does is it models data as a mixture of multiple Gaussian distributions and assigns soft cluster membership. So that means each data point can be belonging to different clusters, and sometimes there is some amount of overlaps or fuzziness among the clusters as well. And then there is dimensionality reduction, and over here again there are many methods, as you can see over here. That is UMAP, then there is PCA, MDS, multidimensional scaling, isomap embedding, then TSNE, then LLE. So these are the different approaches, the models that are there. And what we can do is primarily all these models results in more low dimensional structures. That means instead of taking many features, we look into only a few features which will be having more importance, or which will which will be able to give better predictions and so on. And what PCA does is it preserves the global variance through linear projections, whereas LLE and TSNE emphasizes local neighborhood structure, right? And then isomap preserves global geometric relationships, MDS preserves pairwise distances, and UMAP balances both local and global structure. So anyway, so what it actually tells is there are different approaches based on which we are trying to identify which things could be related or unrelated, and how we can which has got a more effect on the overall thing. So this we will again discuss in detail later. So then there are three association algorithms. A priori algorithm, which generates frequent item set using downward closure property. FP growth is a better and a faster alternative, and it uses a much compressed tree structure, and ECLAT uses vertical data format for efficient mining. Again, we will explain this in detail later. Then coming to semi-supervised model, this as we have discussed, where there is limited amount of levels, then we can go for this kind of models. There is a benefit of this is sometimes when we go for surveys, we can only cover only some sample points and all, but we need to predict for everything else. So particularly land use classification or some building use classification, we can go for that, and then this sort of algorithms will come into will get handy. Now the most common one is model is level propagation. This is a graph based method. Again, we have talked about the node and the edges and how relationships between those could be used to do different sorts of calculations and all. So it's a graph-based method. It assumes nearby points have similar levels, and accordingly it propagates the level, and then it does checks. So eventually, when if the solutions, the results converge, then it is all fine. So then the model gets trained. Now levels spread through a similar levels are spread through a similarity graph from labeled to unlabeled data points, and accordingly we would be able to generate these data points all across this particular for the entire data set, and we form the model which will be used for final prediction. So self-training classifier, this model trains itself by iteratively labeling high confidence unlabeled samples first, and this is of course not graph based but model based, and it uses its own prediction as pseudo labels, and but the problem, and then it goes forward from there. So what happens is initially if there are wrong predictions and all, then this will the problems will increase. So it is sensitive to initial mistakes. And finally, we have got label spreading. It's a improved version of label propagation, and which smooths labels to reduce the noise. And again, it's graph based with regularization, and it prevents overconfident label assignment. Then coming to reinforcement learning, it is a machine learning paradigm which is where an agent learns optimal actions by interacting with an environment and maximizing cumulative reward through trial and error basis. So we have already discussed this. So that means there are different components of it. One is of course the agent and the environment. The agent is acting in this environment, and the environment can respond. So that means the environment can give a reward, or it may also reduce some positives benefits. That means it will give you bad scores as well. Then there is a policy. That means when the agent chooses to do something, that means it is to train itself, it will take some actions. What is the policy based on which it will take the action? What things it will do? In which direction it will go? Then there is a reward. That means once the action is taken, is that good or bad? That feedback has to be there. So this feedback tells the agent about the suitability of an action. And then there is trial and error learning. That means by trying actions not using labeled data, we can gradually check. We can do trial and error based. We can see which are giving better results, and accordingly we can choose those pathways. Then exploration versus exploitation. That means we have to balance between new actions and using good actions. That means we have to do some actions which are not only the ones which are returning good values, but also we have to take risk and add some new actions, because otherwise we'll never know what those will bring in. So there are different reinforcement algorithms as well, but they differ mainly how they estimate the rewards. That is, at the end, at the intermediate stages, or what is the way about that. Then update policies and balance learning stability with exploration. So that means how much of exploration and how the learning happens, those things, all these things matter, and accordingly they have got different strategies or different models of reinforcement learning. So one is Q learning, deep Q neural networks, Monte Carlo method. We were discussing those earlier. Temporal difference, policy gradient, professional policy optimization, and SASA, state action reward, state and action. Finally, we come to neural network based learning. So these are computational models inspired by the way our neurons are connected in human brain, and how whenever we get any stimuli from the environment, our neurons fire, and it is not a single layer of neuron, there will multi-layer of neurons, and eventually it comes out to form an opinion of that stimuli, or then it acts upon it. So that this is inspired, this particular approach of solving or looking into a problem is inspired from human brain. And we can learn very complex patterns following this particular approach from data. And this is also results in, eventually these models that are using neural networks, we have developed many deep learning models which are very intelligent and it can take very complicated decisions. So, what it does in this kind of neural network models, what we do is basically we establish a relationship between high dimensional and unstructured data. From high dimensional and unstructured data, and what these relationships actually help us to understand the connection between this all and how we are getting a particular result. Now, this relationship has to be definitely non-linear. So it's not a linear relationship. Linear relationship are easy. You don't require neural networks for that. But only in cases where the relationship is very complicated, there are many layers to it, then we'll go on neural network. Then we can extract automatic, automatic feature extraction is a part of, is a part of neural networks and all. And then supervised, unsupervised reinforcement learning, all could be, taken up using this, neural network approach as well. So what are the different types? There are many types actually. Some are autoencoders. Then there are recurrent neural networks. As I was telling you earlier, that when there is time series data and all, where the previous data has to be remembered, and then that is where recurrent neural network comes in. Deep neural network basically is more advanced version of neural network with many layers and so on. Then convolution neural network, it's mostly about image processing and all these things. And within that, there is transported convolution network and deep convolution network. Similarly, we have got several categories like the regular RNN has got long LSTM is one thing, gated recurrent unit GRU is another, modeling approach and so on. And then there is generative adversarial network such as GAN, Wasserstein GAN, PsychoGAN, then deep convolution GAN, DGGAN, conditional GAN, and so on. So this is where we can also generate new information. Then there is transformers, that is where the entire feature set is being looked upon together and then a decision is being taken. So that's the transformer approach. So this is now becoming very, very important, particularly in large language models. And large language models like, you already know Perplexity, ChatGPT, and all these different models. These also are a class of deep learning models. But of course, the model, when it is built, it utilizes different types of approaches all combined together, right? And but we can say it's a class of deep learning models, and it is built using the transformer architecture, and it is trained on massive data, so that when the model is trained, it has got billions or millions of parameters, and each of this will be able to predict whatever needs to be generated, right, in form of text. After a particular word ends, you can generate the next word, or it can make sense of the context and can generate the the entire sentence or even the entire paragraph as well. So these are some of the references that we are going to utilize. To conclude, machine learning typology helps us to identify appropriate models based on data, learning mechanisms, and problem context. Thank you.